Yeah, you can try to remember what these equations are. Okay, try to remember these equations. So of course the exam is now open everything. So for you guys, the important thing is just remember where to find the equations. You have the book, know where this equation live in the book. If you don't have the book, then I guess know on the slides how to find equations. So in the book, this is chapter 3.1, 3.2. So just be sure you can find the equations. Right? So you don't want in the exam to spend 10 minutes looking for equation. Right? There's a lot of equations in the book. You want to make sure you know which are the ones you want to use. Okay. So last thing about ideal transformer is that I remember ideal transformers are entirely reversible. Okay. Primary and secondary is a convention we use. Okay. We normally think of, so the convention we use is for primary, this is power in to the transformer. Okay. Secondary, this is power out. So we have a generator connects to a primary, connects to a secondary. That's normally our convention. But there's nothing in the transformer that says this is the way the power has to go. Okay, transformer doesn't care about this. So, we can flip the two sides, refer to one as primary, one as secondary. Impedance can be referred to both sides. We can, instead of referring everything to the primary side, we can basically take the generator and flip it to the secondary side. Right? We can do all the things. The reason we flip everything to the primary is again just by convention. So we need a convention to know which way it goes. Right? So if you actually building a transformer or you're building a circuit with a transformer inside of it, the direction doesn't matter. You can swap it in and out. It's direction is there's no preferred direction in the transformer. Okay? So when you hear somebody say, "Oh, we have a lot of electric vehicles or a lot of renewables, we'll burn the transformer out because reverse current flow." So you may hear that on some news reports. That's not correct. So it's not the transformer doesn't care. Right? Something else that's going on. Right? So just be mindful when you hear that it's not the transformer. Okay? Some other equipment, which we'll cover later in the class. But just as a piece of technology, transformer is irrelevant which way it goes. Okay, so right, any questions about ideal transformers?
Hi, Professor.
Yeah, go ahead.
And go back to the two slides. Go back.
Sure. This one, power.
Yes.
Okay.
So for the input, like the current and the output current, I1 and I2.
Yeah.
And consider the equation. Let's go back one more slide.
One more slide. Okay.
I1. Okay, so I1. Okay, that's turn ratio. Thank you.
Okay. All right.
Yeah.
Okay. Good. Yeah. So remember, right? The multiply and division of AT is not the same, right? So one is multiplying, one is dividing. So that's why things work out the same. That's why we have AT squared. We talk about impedance. The way it works out. Right? So okay. So that's the transformers. So let's do one exercise. So this is example 3.1 in the book. Okay, so you have the book. You can look at the book. Again, for this class, it's not necessary to have the book. You do fine on the exams, on the homework if you don't have access to the book, if you cannot get one. It's required. Normally, it's required for this time. I will write down all these examples. What the book has is book has more examples. And book has something a lot more in-depth theory than what we do in this class. So it's more material, right? So that's the role of the book. So if you don't have if you cannot get the book, don't worry too much. If you can get the book, it's something that's nice to have, right? Whichever edition of the book you have. So this is example 3.1. So let's look at it. So it says a single phase. Okay, so a single phase transformer is rated at 20 kVA 480, 120 volts, 60 hertz. The source is 480 volts, right? So the source is connected to the primary side. And a load impedance is connected to the secondary. So, and since the load absorbs, so the load happens to absorb 15 kVA at 0.8 power factor lagging. Okay, so this is what we have for the load. And we know the load voltage is 118 volts. So we're going to assume the transformer is ideal, right? So this is an ideal transformer. Then let's look at, so let's find the following question: the load, the voltage at primary. Okay, so the voltage at primary. Source. Connected at primary. So let's find the voltage. B is the load impedance. C, load impedance. Refer to the primary. D, real reactive power supply. By the source. Okay, so this is the whole question. Yeah, so guys, can we not post the links to PDF version of the books in the chat? Just not post this kind of things. You find it, but in the future, let's not try to post this. Right? It's copyright issues. So I appreciate people who posted this. For people who don't have the book, you can look at the link, but in the future, let's avoid this posting in the chat. Okay. Thanks, guys. Okay, so this is a question, right? So let's again read the question. Okay, so for all transformers, we would have a rating of the transformer. We have a rating of the transformer. Basically, this tells the maximum apparent power the transformer can carry. Have a voltage rating, okay, 480 to 120 volts, and has a frequency. So vast majority of the time, the frequency doesn't matter, right? It's just good form to say what frequency the transformer is at. Right? So in the different countries have different frequencies, so we say 60. Okay? The total power, again, is a sanity check because we should not supply more than the total apparent power. So, and then we have a voltage ratio. Okay? So let's do the part one. So what is the voltage at the primary then? What is E1? What is E1? Which equation do we use to compute E1? So what's the turns ratio in this transformer? If it's rated 480, 120, then what's the turns ratio? Right, yes, it's 4, right? So what the rated voltage tells you basically is N1 over N2. Okay, that's what the rated voltage tells you, right? So if AT is N1 over N2, this is E1 over E2, this is 4, right? So a transformer being rated 480, 120 doesn't mean it has to operate at 480, 120. That's just a way of saying what the turns ratio is. Okay, so E1 is AT times E2, 4 times 118. So what angle should we put on this? Right? So there's a phase, right? Because we're talking about real and reactive power. Okay? So to be correct, we need to write a phase to this. Okay? So if but we may just well assume this is angle 0 degrees, right? Because we may just well assume the voltage as the reference we have. So here we'll assume it's angle 0. So what we have is 470, sorry. 472 angle 0 degrees. Okay, so that's our voltage. So again, when you write this kind of complex numbers, it's good form to write the phase, even if it's 0, angle 0, to remind yourself it's a complex number. If in your homework and exam you don't write a phase, we'll assume it's angle 0. Okay, so the question asks for a complex number, you don't write a phase, we'll assume you mean the phase is 0. Okay, that's the conventional we'll assume. So this is part A. Okay, so let's do part B. What is the load impedance then? So this question gives us the power the load is consuming, right? It says 15 kVA at 0.8 power factor lagging. And we know the voltage. So how do I find the load? Do you remember how to do this? Right, so we're given S2, right? And we're given the voltage, E2. And we want to find the load. What's one way of finding the load here? Right, so in the chat, there's some typing, right? So this is Z2 as E2 over I2. There's two suggestions. One is the V square over impedance. One is Z2 as E2 over I2. So the second one is better. Again, because we're dealing with complex numbers. Okay, so when you deal with complex numbers, when you square something, it's a little bit tricky. Okay, because there's complex part, there's real imaginary part to it. Okay, so right, so we score something a little bit tricky. So a safer way is to use the following equation. To say Z2 as E2 over I2. The Ohm's law works for complex or real numbers. So how do I find I2 then? So how do I find I2? Right, so I know E2. E2 is 118 angle 0. Then how do I find I2? From power. Okay, good. So one thing to do is, right, so remember there are a complex conjugate, right, associated with that equation, right? So what we know is S2 is E2I2 complex conjugate. Okay? Right, so let's just, so be a little bit careful with this complex conjugate. So what we have is I2 complex conjugate. This is correct. So this is the equation we have. This is S2 over E2, right? This is what we have. And so it's just, we'll take off the conjugate later. But for now, let's do this question with the conjugate associated with the current. Okay? So S2, right, we said the complex current or apparent power is 15 kVA with a power factor of 0.8 lagging. So what that means is this is 15 K, or let's write out the whole thing, 0, 0, 0. So if we have a lagging power factor, what do I multiply here? What is the angle of this? If the power factor is lagging, right? Yes. So this is basically, we know the angle, we know the cosine of the angle of the power is minus 0.8, right? The power factor lagging means cosine of the angle is 0.8. So here we have cosine inverse of minus 0.8. And so cosine, whether you get it, this minus sign doesn't matter. So you can divide out this 118 and go 0. So what we have is I2 conjugate. I2 conjugate is 127.12, angle 36.87 degrees amps. So this is the conjugate value. So take off the conjugate. I have I2, same magnitude, minus 36.87 degrees. Okay. So we can divide S2 by E2 to get I2 conjugate. Then what we can do is remove the conjugate by flipping the angle. Okay. So this is a process. If you have an advanced calculator, you can plug this into the calculator. In general, you should have something that can compute this sort of complex calculations. Okay. So then what we have is Z2 is now E2 over I2. That's just straightforward complex number division. What we have is 0.92, 93, angle 36.87 degrees ohms. Okay. So the unit of complex impedance is ohms. So C is just as, let's refer this to the primary. So once we refer this to the primary, what we have is AT squared times Z2. So this is 4 squared times Z2. Multiply this out is 14.85. The angle doesn't change degrees. All right, and B, what we have is this is the ideal transformer. So the power supplied by the source is exactly the power consumed by the load. So S1 equals S2. So the power computation is easy. We don't need to do anything. And really for this question, the tricky thing is how do you compute the impedance? Okay. So generally the safest way to compute impedance is to go through this sort of power route. To write out the power equation, S equals to E times I conjugate, and then compute the current conjugate, and take out the conjugate and compute the current. So since again this is remote, right? So so normally for this class you're required to have a scientific calculator just to do this kind of calculations, angles and all this. This is remote, so you don't need to do this in a calculator. If you want to do this using computer, you can do this computer. If you want to do this, using Python or MATLAB, you want to write a script, you can write a script, right? But in the homework and in the exam, you still have to show the equation. You have to still show the steps, right? So it's insufficient to write in your final, I have a script. So given this, I plug into my script, and this is the answer that comes out. Right? So that's not sufficient. If you want to use a computer, you can. That's fine. But just write down the equations you're using. Right? The numbers can come from your computer, your script. So this has happened last quarter. People wrote scripts, and in the final said, buy my script. This is the answer I got, which is not what we're looking for on the final. So any questions about this homework? About this example? Yeah, go ahead.
So is 0.8 the leading factor instead of the lagging? So what should I do with this part?
Oh, so this is leading or lagging. So lagging should be minus, right? 0.8. Yeah. So this is the cosine, and yeah. So this should be minus 0.8, I think. So I will check in the book. I'll check. So okay. So I'll make a note to checking this in the book. I'll clarify. Oh, yeah. Let me check in this in the book. Let me check this in the book. Should be minus. Okay, so I'll check this. I'll check this notation. I'll check this notation in the book. Yeah. Okay, yeah, so I'll take a look in the book. I'll check the sign. I'll check the sign in the book. Yeah, so I think in the example is 0.8. I will check to make sure in the earlier part, the definition is also this one. Okay, all right, okay, so let's see. So let's take a break now. Let's take a 10-minute break, because after this, we'll go into non-ideal transformers. Okay, so after this, we'll go into practical transformers. So let's take a 10-minute break, come back at the 10:22. Okay, so next hour, we'll go to practical transformers. Okay, thanks, guys. Okay, so let's get started for the second half. So second half of the lecture, we're looking at the practical transformer model. So just terminology, this is sometimes called non-ideal transformer or practical transformer. Right, so you see both. And practical transformer basically means, let's look at some of the assumptions that we made for ideal transformer that was not so practical. So let's look at the first assumption. Let's look at where we made assumption, right? So let's look at the windings. Okay, so let's look at the windings. So what does a winding look like? Basically, what the winding looks like is you take a wire and you do this kind of thing, right? So you wind it up and let's flow some current into it. So what does this look like? So you take a wire, just have windings.
An inductor.
Right? So this thing looks like an inductor. So in the ideal transformer model, we totally ignore the fact that I have an inductor here. Okay, I just ignored it. But this being an inductor, what it does is have its own flux going through this inductor, right? But not all the flux that's generated will go circle around the transformer. This inductor will leak some flux, right? This is called a leakage model. Okay? So what we have is we have leakage flux coming from the fact that I have my own inductor at both of the windings. So then the total flux is the following. So the total flux I have is the flux that I leak at one, that goes through the inductor, that doesn't go through the transformer, plus whatever is generated inside. Then I have the same thing at 2. So if you look at the total flux at 2, this is what I have. So what I have is, so I have this kind of leakage flux. So what this shows up, it shows up something that's in series. Okay? Because if you draw this thing, if you draw this model, what we have is, if you look at the voltage, right? The voltage depends on two things now. It depends on the time derivative of the flux. This is Faraday's law, right? Plus whatever resistance I have on the wire, right? Because if you look at my wire in the winding, the wire is not a perfect conductor. So what this will look like is some resistance plus some inductor to me. So this is R1. R1 means whatever resistance I have on my wire. So if you take a time derivative, this becomes 3 parts. So let me write the series resistance first. So this is the fact that how I go through the current is not, the wire is not perfect. Then I have some inductor sitting here. And then this is the inductor. This is the inductor equation plus the ideal transformer equation we had before. Okay. So this is what we have for the V1. V2, we can do the same. This is time derivative of the flux IC minus R2, I2. The minus sign comes from the fact that the current is flowing out of V2, right? So there's a minus sign. As where basically the current reduces, sorry, the voltage reduces by this current flow. So this is minus R2, I2 minus L I2 dt plus N2. Okay, so this is my equation for taking into account that this is not a ideal transformer. So I have some things that's in series, right? So I have some non-ideality in series. So then if you draw the whole thing, basically what we have is, I have an ideal transformer sitting in between the primary and secondary. And what I add to make this transformer more practical is I add a R1 and the L1, basically, to make it right? To reflect the fact that my windings, my wires, the fact that I'm winding a wire on the transformer creates a inductor, basically. I have some resistance of the wire, and the way I make it creates an inductor. So that's why I have these two elements on the primary side, and similarly two elements on the secondary side. So this is a more practical transformer model because we relax the assumption that we made that the wire was perfect. This is not a perfect wire, so I have this two, 4 additional elements that comes in. Okay, so in the middle, I still have this ideal transformer. Any questions about this? For adding these 2 elements? Okay, so I guess on a practical note, or this practical transformer, as we don't compute the values this way, we don't measure the flux and take a derivative, right? So the way this is modeled is once you build this kind of transformer, you can just do a circuit measurement. So once you know this is the model we have, you can try to measure the inductance of the transformer. So this is what, so this basically takes care of the fact that the windings, right? We have some flux leakage from the winding and some resistance on the winding. What other assumption did we make on the ideal transformer? So what other assumption did we make? Right, so remember at the beginning of class when we reviewed it, we said the transformer depends on 3 factors. Right? The area, the surface area, the mean length of the circuit within the transformer, and the permeability. Right? So we made the assumption that the permeability was infinite, but of course it's not. Right? So we don't have perfect materials. So transformers are normally made by steel. It turns out steel is a good material to make transformers of. But however you make it, it's not a superconductor. So this has finite permeability. So the fact that we cannot assume the current actually adds up. So this is not 0 anymore, right? So the net current balance is not 0. Okay, so let's look at what we do to this current balance equation. Let's look at what we do. So the way we analyze this circuit is we'll make the assumption that let's look at what happens when the secondary is an open circuit. Okay? So let's say we have some transformer, right? So this is I1 into it. This is I2 coming out. We're going to open. We're going to leave this secondary side open. Okay? So if it's an ideal transformer and you leave the secondary open, there's no current flow because I2 is 0. Right? But since this is not an ideal, right? This is a more practical transformer. So there'll be some current, right? That's actually goes so-called into the transformer. Right? So there's some magnetizing current that's there. So let's look at what happens in the magnetizing current. Okay? So let's look at what happens is, so IM, as you can think of the current flowing this way. Okay? So this is now RC phi C over N1, right? So my current has, if I open it, the current has to go somewhere. So the total current I have is actually 2 parts. So if I have current flow, then it's IM plus N2 over N1 times I2. Okay, so I have this extra term, IM, modeling the fact that this sum is not 0. Okay, so the sum is not 0. So there's a little bit of mismatch. Let's look at what happened to the mismatch. Okay, so we have a mismatch. Basically, what we have is we again have something that looks like an inductor in between, right? Because if I know my current, this magnetizing current, this current in parallel, is this number. Then I know my field is again a time varying field, right? So phi c is time varying. Okay? So I take a derivative. This is, okay? So this is Lm dim dt. Okay, so I have this sort of time varying field inside of it. And then if you look at the constant in front of this Lm becomes n1 squared over Rc. This is the constant that lives here when you take a derivative. So let's write one more step out of here. So this is n1 d phi c dt. So this is equal to Lm dim dt. So you substitute the equation for phi c into this voltage equation. We get that we basically have a magnetizing inductance, right, sitting inside the circuit. So in addition to having this sort of elements in series, what we have is we have elements both in series and in parallel. Okay? So this is this IM, this LM capture the fact that when we have sinusoid current flowing in the transformer itself looks somewhat like an inductor. Okay? Whenever we have sinusoids, we have sinusoidal current flow, and this flowing through a conductor will look somewhat like a inductor for us. Okay, so this basically relaxes the assumption that we made. The core is a permeability as infinity, and of course, whenever we have current flow, if it's not perfect conducting, we also have something that's called the core loss, right? So when we have current flow, basically we'll have this resistance inside the core. Right? You heat up the transformer whenever we flow. There's a induced current flow. So this current flow heats the transformer up because it's not a perfect transformer. It's not a perfect superconductor. So we have this Rm in parallel as well. Okay? We have this Rm in parallel. So the final, I guess what we have at the end of the day for this kind of transformer model is we have this ideal transformer. Okay? This is our easy to understand ideal transformer. Then we start put things around it. So in this case, we put a inductor and a resistor in series, right, at both sides. And we put a Rm and Lm, this core inductance and core losses, in parallel. Any questions with this model? Again, this is still actually a model most of you should have seen before, the kind of transformer model. Okay. All right, so let's do one. Okay, let's think about. So for the things in series, right? For the L1, R1, L2, R2, I have on both sides of the transformer, both in the primary and secondary side. Should I have the core elements also on both sides? Right, so here I'm drawing the core elements on the primary side. Should I have on the secondary side as well? For symmetry? If no, why not? Right, why is it that for the things in series I have it on both sides, but now in parallel I don't have it on the other side?
Because it's happening in the transformer, which is the interaction.
All right, can you speak up? All right, I'm a little bit of trouble hearing.
Because that stuff is for what's inside the transformer, which is both sides interacting at once.
Right. So what I had is, remember, this is for the entire transformer, right? So this is capturing the fact that the whole transformer is not ideal, right? So for the windings, I have two windings. So here I have one transformer, okay? Then this brings back to a question that, well, I said the transformer was non-directional, but this drawing makes it look like we made a choice to put this in a primary side, right? And in fact, this is a choice we made. Okay? This is a choice we made. This is not anything to do with the transformer should show up as a primary or a secondary side. We could have easily put this into a secondary side by reflecting this impedance to the secondary. Okay, we could have done that. We're just to choose to draw this in the primary side because we're going to refer everything to the primary side anyways. Okay, so there's no reason to draw this in the secondary side. We may just well draw in the primary side to refer to it. But again, this doesn't mean there is now somehow, primary side is special in any way. Right? This is just saying that, for circuit analysis reasons, we draw this on the primary side. Okay, but these two models are core, right? The entire core of the transformer. Okay? So this is the circuit model we have. Any other questions? So in the next homework, you'll be seeing this quite a bit, this kind of model quite a bit. Okay. So of course, we can do everything now with a sinusoid steady state. Right? We can now do a steady state analysis. Basically, instead of looking at L inductance, we can look at things like J and JX1. Okay? And so we have series branches represented by impedances. We have shunt branch. So this is called a shunt. Anything in parallel in this terminology is called a shunt. So what shunt refers to as this element. Okay, so this is JC, and here we have minus JB. Okay, so this is referred to as shunt. And there's actually a slight difference between how this is referred in convention. So in convention, what we have is we have in series. So things in the series branch are impedances. And we have what we have in the shunt. These are represented by impedances. Okay, so there's a so that's why what you see as in the shunt, we talk about GC rather than RC. Okay, so this is how the admittance we talk about. Right? So this is just the value what we talk about. Okay? So there's a reason we do this. Right? There's a reason why it's easier to talk about, for example, things like conductance than resistance. Right? There's this reason. So you gotta think of why. Why is it we choose a sort of different symbols? We choose different conventions for things in series and for things in shunt. There is a reason, actually. There's a reason. It's just not just to make your life difficult. There's a. Can you think of this as a reason why this is done?
They're easier to add.
So one is they're easier to add. So sometimes it saves your inverse. That's not necessarily always the most important thing, right? Given nowadays it's all added by computers anyways. So. Okay, so the reason is actually quite simple. The reason is when we see, so this is a practical transformer, right? So I want to say, okay, when you make, how do you get to ideal transformer going from in practical transformer? And the thing we want to say is we want to say something goes to 0, then I have ideal transformer. So for example, R1 goes to 0, means I have no resistance. X1 going to 0, I have no inductance. Now, if this was a shunt resistance, I cannot talk about going to 0, okay, because then I short the circuit. But I still want to say when things going to 0, when things are small, I recover my ideal model. Okay, so I talk about G being 0, means I have an open circuit. I talk about Bn being 0, I have an open circuit, right? So in engineering language, we often want to say that when non-idealities are small, right? Then I recover the ideal model. So the practical model is a small perturbation of my ideal model. But then if we talk about shunt resistance, I would say the shunt resistance is actually infinity, right? It's an open circuit. So for ideal transformer, I don't have the shunt, so it's an open circuit. So that makes the language a little bit tricky to talk about. Okay, so for the reason that I always want to say when things are small, I require my ideal model. This is a convention we have. Okay, so it's actually very powerful ingrained things into our minds that small things should be close to the ideal model. Okay, and that's the thing we follow. Right, so that's just a notation we use here. Okay, so that's the makes basically all this comes from once it's small perturbation, it's okay. Right, when things going from 0 to a very small value, it's okay. Use the ideal transform. Okay, so that's why we talk about things this way. Right? So just when you do your homework, be a little bit mindful of how the shunt is given. Okay? Be a little bit mindful of how shunt is written. Right? So in the homework, we'll try to make this clear. Right? But that's something to keep in mind. Okay? All right. So this is the circuit we have. Any other questions about this circuit? Okay, so we'll have this circuit. This circuit is still not the best circuit we can have, right? Because what happens is, what we have is, there are still things on both sides of the ideal transformer also. Okay, right? There's still many things here. So let's make things a little bit easier for ourselves. So the first thing we do is take everything from the secondary and refer to the primary. Okay, just do that. Okay, so the first thing we'll do is to make our life a little bit easier is to write everything into the primary. So what we have is, so we still have an ideal transformer. So let's draw that thing first. So this is our ideal transformer. But there's nothing on the secondary side anymore. I'm taking everything to my primary side. So if I refer things to the primary, then there's a secondary resistance that comes out. There's a secondary impedance, sorry, the secondary reactance that gets reflected to the primary. So this is N1 over N2 squared R2. This is J N1 over N2 squared X2. Okay, this goes to the second primary side. I still have my shunt elements here. I have my original primary R1, JX1, V1, right, so this is GC minus JB. Okay. So that's what we have as a circuit, right? So I have I1 going this way. This draws shunt element, draws some current. Okay, so, sorry, this is. The shunt element draws some current goes in here. So this is some current that's being pulled into the shunt. And the I2 comes out this way. Okay. So this actually we don't lose anything by doing this reflection. Just makes our life easier. Okay, we don't have to have things on both sides of the transformer anymore. So this is one thing that's easier for our life. We do. And the next thing we do is actually a simplification. Okay, we'll make a simplified assumption on this. Next we do is we'll ignore the exciting current. This is basically this is a fancy name for shunt current. Okay, so we'll ignore the shunt current. Because if you think of the transformer being a core, right? So normally nowadays there's the manufacturing technology is pretty good. So it's almost ideal. So when you take the core parameter into account, the answer you got, the changing answers, all the calculation will do is less than 1% normally. Okay? So since the change is so small, and this actually shunt makes our life difficult because this circuit is actually still quite a bit of work to analyze this circuit, right? You have things in parallel, you have to do things in parallel twice to get this, to do the current and voltage analysis. So the next simplification and the simplification we make a lot of times is to just ignore the shunt. So there's no shunt anymore. And without the shunt, actually the circuit looks very nice. Because now we can just add the resistance and the inductance, right? We can add, so we have a equivalent. We now have equivalent impedances on the primary side of the transformer. So again, on the secondary side, we have nothing. I1, V1, okay? And what we can do is we can just add it R2, X equivalent is X1 plus N1 over N2 squared X2, okay? So this is another assumption we can make. And this is very commonly made. And this is very, very commonly made because the core things are, makes your life 5 times more complicated, but doesn't, with, again, that's within 1%. So we'll make that assumption. The core go away means all the parameters are small, right? This now looks like an open circuit for us. And then the next assumption we can make is, right? So after you make the assumption that core doesn't exist, we add things together. And the next assumption we can make is, so the next good assumption we can make is, if you look at the wires. So if you have a wire that has this kind of winding, then normally the inductance is more dominant. Okay, so it looks like a resistor in series with inductor, but normally it looks more like an inductor than a resistor. Okay? The next assumption we can make is we can ignore the resistance in the wire. So those are generally not large compared to other resistors we have in the system. Okay? So if you ignore this, then things becomes really simple. So this is Jx equivalent. So X equivalent is just X1 plus the secondary things reflected to the primary. Okay, so this is the equation we have for simplified models. Okay, so if you simplify this more, of course, so any more simplification, you recover the ideal model, right? So this is the simplification where we will. So when we say simplify, this is sort of the simplest one we have. We just have the fact that you have inductor left over in the windings. The next more practical one is you ignore the shunt, and the full practical model is you include shunt as well. Okay, so these are the circuit models we have for the transformer. Any questions about this simplification we make? Okay, so when you do a homework, you will again, so you will most likely be told which model to use. Okay, so if you do a homework or exam, the question will say ignore shunt, then please ignore shunt. Right? If the question says use the full model, then use a full model. Okay, so read the question carefully, look at which of the model you should use. Okay? And so when you need to do a quick and dirty calculation, normally you just use this one. Most of the time we'll use this one. We'll use this one without shunt. Okay? The one with shunt is a calculation I guess you do once. But then for other times, we rarely have shunt in transformers. For most transformers, we just ignore the fact that we have shunt. Okay. So no questions. Let's do another example then. This is example 3.2, following along in the book. Okay, so this basically is the first example now with some Okay, so this is first example, but with a more practical transformer. Okay, so let's look at how we do calculations with this more practical transformer. So let's say I have a single phase transformer. This is again 20 kVA, 480, 120, 60 Hertz. Then basically we do the following. So the idea is let's do a short circuit test. Okay, so we're going to do a short circuit test with this transformer. Okay, and then I apply a rated current as the primary. Okay, so apply a primary. Okay, so I'm going to short circuit test. Let's just apply some current into it. Let's see what happens. Then what I observe is we measure V1 is 35 volts. P1 is 300 watts. Okay, so this is our result when we do a short circuit test. Now let's do an open circuit test. Okay, let's do an open circuit test. Then apply rated voltage at the secondary. Okay, I apply a rated voltage at the secondary. Then I measure I2 equals to 12 amps. P2 is equal to 200 watts. Okay, so these are the two tests we do, right? So normally when we do a circuit test, we do a short circuit test and open circuit test. That basically helps us to estimate all the parameters in the circuit. Okay, so we do it for a transformer, we do the same thing. We got a transformer, put a short circuit, measure a bunch of stuff, have an open circuit, measure a bunch of stuff, and then look at, how do we compute the rest of the parameters. So let's see what we can calculate. Okay, so the first part, still neglect shunt. Okay, so shunt makes things a bit difficult. So let's say we have no shunt circuit in this. Then from the short circuit test, find R equivalent, X equivalent. Okay, this is from the short circuit test what we do. Then B, let's say from the open circuit, from the open circuit test, find YM. This is the admittance, DC minus JBM. Okay, so from this two tests, we want to figure out basically all the parameters we use in this model, right? So for in this one, sorry, not in this one. So we'll find all the two things. We want to find the equivalent model, and we want to find the short circuit. Okay, we want to find this. We want to find the shunt values. We want to find the equivalent resistance, equivalent impedance, and the things in shunt. Okay. All right, so let's see what happens when we do this kind of test. Okay, so let's do question A first. So the problem says when we do the short circuit test, we give rated current. So what is the rated current for this transformer? So you look at the question, it doesn't give you the current rating, gives you the voltage and the power rating. So what is the rated current for this one? right? So I have rated power, I have rated voltage. How do I compute the rated current? Yeah, so the rated current is just the power over the voltage. Okay, so it's exactly what you think this will be. We're applying this as the primary, so we're going to use the primary side rated voltage, 41.67 amps. Okay, so this is our primary thing. All right, so now if this is my rated current into it, and I measured a bunch of, right? So if you look at the short circuit, so what short circuit is basically this. I apply a current. We're going to ignore shunt, so this is my circuit. Okay. Then I short the secondary, so this is what I have. So if this is my rated current, and I'm told the power consumption and the voltage, then how do I compute the R equivalent and X equivalent? Can I compute R equivalent? I think about this. Let's see which one is easier to compute. Okay, so let's compute the resistance. How do I compute the resistance? How do I compute R equivalent? Right, so I know the current, right? So I know this current going through it. I know the active power we have consumed. So in this short circuit test, this resistor is the only thing that consumes active power, right? There's nothing else that consumes active power in this circuit. The inductor does not consume P. The secondary is shorted, so there's no power loss there. Okay? So the active power is only consumed by this resistor. That's what allows us to compute R equivalent first. Okay? So then how do I relate active power consumed by this resistor to the fact that I know the current? How do I do that? Okay, so let's remember. So I have some resistor. Okay, I'm flowing some current through here. I know the current magnitude, but I don't know the current phase. Can I know the power being drawn from this resistor? What is the power consumed by this resistor? I know the, right? So I know the current, right? I know the magnitude of the current, right? So from the rated current, we know its magnitude, right? The phase, we don't quite know the phase information yet because we are complex impedance. Okay? So what we have is the following, right? So from this resistor's perspective, the phase doesn't matter. Right? I'm a resistor. I don't care about the phase of the current flowing through me. So the power dissipated through this is the squared. So this is a magnitude squared times R. Okay? So always a magnitude squared times R here. Because I have the magnitude of the current. I have I squared R loss through this resistor. The phase doesn't matter to this resistor. Okay? So what I can use is I can use P equals to I magnitude squared times R equivalent here. Right? This is what I have for I squared R. Right? I squared R loss through the resistor. So I have the same thing for this resistor. So this I have as P over I squared. Okay. So this is how much I have 300 watts being dissipated. I have 41.67 things squared. This gives me 0.172 ohms. All right. So remember to square the current. So the answer in chat is almost right, except remember to square the current. Okay, this is I squared R. Any questions about computing this equivalent resistance? Okay, so now how do I compute the impedance? Right, this is, we're not entirely there yet. Right, question says find the R equivalent, X equivalent. So now I have my R equivalent, but I don't have my X equivalent yet. And the problem is, this question says I measure the voltage to be 35 volts. It doesn't tell me the phase information. Right? It doesn't tell me the phase of the voltage and the current. So as I apply rated current, I measure 35 volts as the input. Okay. So what we have is the following. What we have is, I know this magnitude is 41.67 amps. I know my voltage magnitude is 35 volts. Okay, I measure this kind of things. I did not measure phase. Okay, I did not measure phase. Okay, I can measure power consumption, of course, but so is there a way to find out the X equivalent? Can I do it? Do I have enough information? Okay, so let's look at this. Let's remember Z, right? The impedance is voltage over current, right? But we have a complex impedance. So since I don't know the phase, I cannot exactly use this equation, but this is fine. Let's take a magnitude over all the variables. So this I can do, right? I can figure out the magnitude of the impedance. Okay? So this is 35. This is, I can do this, right? We know this. So I can find out the magnitude. This is 0.84 ohms. Okay, I can find the magnitude. Any question about this stuff? Finding out the magnitude? Okay, so how do I find the so if I have the magnitude, how do I find the imaginary part of this? I remember this magnitude. Okay, right, so remember Z equivalent is R equivalent plus JX equivalent, right? Is what I have. So what I have is I can, the magnitude, so okay, let's do a complex number equation. The magnitude is the magnitude of the square of the magnitude as this sum of the squares of the real and the imaginary part, right? Okay, so I know these two parts, right? Okay, so then what I can do is from this, I have X equivalent is the square root is the square root. I now know all the information, right? I know what the square root of the magnitude is for Z equivalent. I know what R equivalent is. So plug everything in, we can figure out this is 0.8 ohms. Okay. All right. Any question with this calculation? Okay, so this basically this kind of calculation, one is not difficult per se, but does require us to remember a bunch of relationships between this kind of variables. Okay? How it basically says, if you know the magnitude information, how do you get the complex part out of this? How do you get the imaginary part out of this? So this seems to be making your life more difficult than it needs to be, right? Right, because if I could be nice and measured the phase information, I can tell you the voltage, right? Instead of just measuring the magnitude, I can tell you the phase. Your life will be much easier. You could just divide, voltage by current. I don't need to go through this sort of squared and taking square root calculations. So why in practice we don't measure phase information? So most likely, if I give you a transformer, you'll be doing the same measurement, doing the same calculation. But why is it we make our life more difficult in the calculation part? Why not just measure phase?
Because the time intervals are really small, is that it, or?
Right, because phase is actually very complicated to measure. Right? It's not easy measuring phase information. Because think about it, right? How do I measure magnitude? Very easy. You take M meter, plug in there, you read the sinusoid out of it. You basically measure the max to the mean for a few cycles, and take an average. That's your magnitude. Power is used to measure as average quantity. Let's measure power in the average quantity. Okay? Similar with current. Phase is hard because what phase asks you to do is to measure phase, you need a reference. Okay? Everything is 60 hertz. So just reading the sinusoid by itself doesn't help you with phase information. Everything 60 hertz will be reading a sinusoid. Okay, this doesn't help you. To measure the phase information, you need a reference. You need a zero clock. Then you need to watch where things cross zero to get the phase information correct. Okay? And to do this, if we have a 60 hertz signal, okay, so this is 60 hertz. Then to get a reasonable measurement, you have to measure at least a couple times per cycle to have anything reasonable of a phase measurement. Okay? So that means you basically have to measure something, let's say at a hundreds of hertz or kilohertz measurement. That is expensive. Okay? That you need an oscilloscope, and you have to tune the oscilloscope. So a voltmeter, for example, is like $30. A good oscilloscope that can do high power, reasonably high power measurements is $10,000. Right? So it's state of the art, so on. So a oscilloscope is not easy to buy; it's expensive. So for practical purposes, phase measurement is actually not typically done in practice. Even for very large scale systems, most of the time we measure magnitude. We can measure P, Q, and the magnitude of things. These are average quantities. We don't need timing information. Phase requires us to have timing information. So your life is made difficult, not by we want to be mean in the questions, but test whether you know all this kind of information. It's just it's just hard to measure phase. Okay, it's very hard to measure phase. Okay, so let's do question B. Question B comes from a similar thing. I cannot measure phase very easily. I can only measure average quantities. Okay, so let's basically, when we measure average quantities, how do I find things from average quantity measurements? And the calculation basically is very similar to the first part, right? Because let's say, so what this circuit is for part B is the following. Part B is simply part A written backwards, essentially, a little bit backwards. So it says, look, let's say I have a shunt, wrong way. I have a transformer. Let me put a voltage through this part and look at what happens. Okay, so I put in a rated voltage as the secondary, right? I'm putting a rated voltage as secondary. So this is 120 volts. And then if I reflect this to this part, what I get is this is 480 volts, basically. I have a 480 voltage at this side. Then once I have a 480 voltage at this side, I can do the rest of calculation. So this is GC, this is BM. Right, so, and I'm given the fact that my current flow in this I2, right? So I know my current flow into I2. So I know I know I2 flowing is 12 amps. I know P2 is 200 watts. But for this part again, V1 is 480 volts. So I have GC, the conductance, the GC is P2 over V1 squared, right? So remember V1 squared times G equals to power. Since this admittance is the only thing that we can dissipate power this way, then doing this calculation gives us this is 200 over 480 squared. This is a very small number, 0.00087. What is the unit of 1 over resistor? Anybody remember what this is? What's 1 over ohm? Siemens, that's right. Yeah, so sorry, Siemens and mho. So yeah, so SI unit uses Siemens for this. So this S for Siemens. Basically, this is just 1 over ohm. Okay, so this used to be called a mho, ohm written backwards. That's no longer the standard. We want to appear to take ourselves a little bit more seriously. So we change the standard. We create this value called Siemens, and we're just gonna use this. Okay? We have to show we have more self-respect. But mho is seriously a better unit, in my opinion. But it is what it is. So Ym, similar calculation as before. This is I1 over V1 for Ym. So this is N2 over N1 squared I2 over V1, plug all the numbers in. This gives us this whole thing as 0.00625 Siemens. Then Bm is the same calculation. You take Ym squared minus Gc squared. This gives us a value of 0.00619. Okay, so this is the exact same calculation, right? And here, as expected, the value should be small, right? So this, we want to say the shunt is almost like an open circuit. That means the admittance is very small. Right? Admittance 0 means open. So as expected, all this number should be small, right? So 0.00087 is a small number as we expected in this case. All right, so should we do the next example? Yeah, next example may take a bit of time. So, okay, so we'll do the next example next time. But so let's finish this class, 5 minutes left. Let's talk a little bit about how do we measure phase as a practical situation. So let's say you're a grid operator and you really, really want to know the phase of the current or the voltage you have. Okay, so let's say you're operating BPA, which is the transmission network for us, as a transmission network operator for us, Bonneville Power Authority. And somebody said, okay, we should really measure phase, right? So we, knowing phase is useful information. So how do you think BPA actually does it? How do we do time stamping in a big system? Right, so BPA covers the Pacific Northwest, so Washington, Oregon, and Idaho, and the sort of big Pacific Northwest areas. Unless I have a generator in Portland, I have a load in Seattle, and said, okay, I want the phase difference between these two buses for various reasons. How do I compute this phase difference? How do I do a time synchronization? Atomic clocks. So if we had enough money, we'll do atomic clocks. BPA does not have this kind of money to do atomic clocks. So what's the next best thing to atomic clocks that we can do? Basically, the idea is correct. Basically, I need to synchronize a clock, right? So we can both do sinusoidal measurements at different buses. as long as we have a perfectly synchronized clock, then it's fine, right? Then it's fine. Because if I have a perfectly synchronous clock, I can look at my sinusoid to see 1 cross 0, look at other sinusoid to see 1 cross 0, measure the difference in time, then that will give me the phase information, because I know this is 60 hertz system. Okay? So atomic clock is one way to have a synchronous time. Turns out that's right, a little bit expensive. So the next best thing is GPS signals. So all the GPS actually is time synchronous. So the GPS turns out general relativity matters for the satellites. So they all need to do time synchronization to do correction. So actually in the grid, what we do is we use GPS signals. GPS signals are synchronized pretty well. Now the propagation time of signal over a long transmission line affect the apparent phase difference. Right. So not really. So GPS signal is correct to about 1 microsecond or so. And turns out for the grid applications, having an accuracy of or precision of a few microseconds is good enough. And normally the transmission line, right? So that transmission line creates a standing wave. So the standing wave propagation speed is fast enough. That's below a few microseconds, right? So basically, what GPS gives us is a few microsecond accuracy, and that's normally good enough for phase measurements. Okay, so for phase measurements, what we do is we piggyback on GPS for a synchronous clock, then we measure, then we know the phase difference. So all of these systems now in the US will have at least a few, this so-called phasor measurement units to do this kind of measurements. It's still fairly expensive, right? Fairly expensive. So so we only have a few, but a big topic of research is, one, how do you make this kind of things cheaper? Two is, what do you do when you have this sort of good synchronized measurements? Right? There's a lot of applications for good synchronous measurements. So that's what we do in system. But vast majority of time, your calculation still be something like the calculation we did today. So if this seems complicated to you, imagine doing this kind of calculation for a system with 1,000, 10,000 buses. That's a lot of the challenge about this course is about. Basically, how do you do this kind of calculation? These are not linear. They have squares and magnitude and square roots. How do I do this fast and robustly for a very large system? Okay. So there's some hint of the calculation we'll be doing latter part of the class. We basically use matrix and vector notations to do this kind of calculations. Okay. So we'll stop here today. A reminder, if you haven't taken a look at homework, do take a look. It's a little bit long, so you don't want to wait until Wednesday and do everything on Wednesday, right? So take a look. I will have office hours on Tuesday, tomorrow, if you have any questions. Right, so I'll stay a little bit after class, but other than that, see you on Wednesday.